theoretical quantum optics from JIT Noida with Professor Anirban Pathak. And then in 2018, I completed my PhD, and then I joined as postdoc in Pulaski University, Olomouc. I'm currently working here for last more than 5 years. So today I'm going to talk about some of my recent works and an overview of them and their applications, potential applications in different aspects of quantum technologies. So my topic is, that's why my topic is quantum optics for technology. And so to begin with, I will start briefly by explaining what are these non-classical states, which are quite important in quantum optics. And then I will give a few examples of their generation from Raman process, and then we'll discuss some of our recent works on non-Hermitian Hamiltonians in multi-mode bosonic systems. Finally, before concluding, briefly mentioning our collaboration with experimentalists for generation of some engineered quantum states. So to begin with, most of the photonic quantum technology, that it relies on some special kinds of states, which we call non-classical states. They provide this advancement or like advantage in quantum information and quantum technologies in generally, and they are characterized by these negative Glauber-Sudarshan P function, and which is defined when a density matrix or a state is written in coherent state basis. Then this P function, when the state cannot be interpreted as mixture of coherent states, and that is characterized by the negative values of P functions. And alpha here is the coherent state, which is Poisson distribution of number states. For example, I have shown here, and given the density matrix and the P function, its quasi-distribution function, so we can always obtain the corresponding photon number distribution by sandwiching it between the Fock states in this form. So for example, for coherent state, for beta equal to 2, we have corresponding Glauber-Sudarshan P function as a delta function, and corresponding photon number distribution is given by this blue curve. And so Poissonian nature is visible here. But when we add a photon to this state, so we know that the probability for obtaining zero photon in the measurement becomes 0. So which I have shown written here as P0 is 0. And in that case, we, from the right hand side of this, we know this will be the quantity in terms of P function. And we know that the second term cannot be negative, it is greater than 0, so it is positive. So that makes sure like certain values of P are negative to make the whole quantity 0. So this is one example where we can clearly see that P function is negative for the non-classical states. And this also shows non-classical nature of photon added states. So this example was for photon added coherent state. So similarly, we studied such theoretically we studied generation of such non-classical states in different physical systems during my PhD. For example, optical couplers, optical cavities, etc. So there are so many examples where these kind of states are useful. For example, teleportation, where quantum state is transmitted to a distant party using previously shared entanglement, and so entanglement is used as a resource. Similarly, in the other aspect of quantum communication, so a dense coding where previously shared entanglement is used to transmit 2 bits of communication, 2 classical bits by using one travel qubit between the sender and the receiver. Another aspect is quantum cryptography, where, for example, the BB84 protocol that requires single photon sources, which are highly non-classical. And quantum computing, for example, which uses qubits or photonic qubits for photonic quantum computing. So In all these aspects, so we require non-classical states. And there is one aspect of computing, because there are so many other architectures where computing is can be achieved, but there is one aspect which is secure quantum computation, where communication features of communication as well as computations are required, and their photonic qubits are preferred. So as I mentioned, for PBAT4 protocol or quantum cryptography, we require single photon sources. So they are characterized as anti-bunching. For example, this is characterized. This is measured in experiment using HPT experiment, which is Hanbury, Brown, and Twist experiment, which requires us to measure the second order correlation function. So, for example, this is a source. From this sample, we have the light that we want to characterize the source from the source, and so we use a beam splitter and the two detectors at the two outputs. And so we vary either the distance of one of the detectors, or that we like vary the time on the counter, and then by varying this tau for different values of tau, we obtain this quantity, and from that we obtain this quantity g2 tau. And so g2 tau can have this kind of variation for different kinds of state. For example, ordinary thermal light, which is at the moment in the room as well, there, and my room as well. So there the beam splitter splits the light equally, and then we have a peak at 0, tau equal to 0. But for laser, it is supposed to be more like a flat line. But for non-classical or ideal single photon sources, we have a dip at G2 0, for 0, tau equal to 0, which characterizes anti-bunching of the source. So effectively, the way we define anti-bunching is if G2 0 is less than G2 tau for non-zero tau. So effectively, we see from this dip that if we have G2 tau, G2 tau greater than G2 0, then we call the source anti-bunch. So the other aspect that I mentioned is useful was entanglement. So entanglement is superposition in tensor product space, which fails to satisfy separability condition. So in other words, it means that we can't write individual states xi1 and xi2 for a system which is defined in Hilbert space H, like which is tensor product of two small Hilbert spaces. So in aspect of single photons that I was mentioning earlier about anti-bunching, so if we are given a photon number entangled state, for example, from spontaneous parametric down conversion, and then we can measure one of the beams and then get a single photon or photon number state in the other beam, which has one more example is quantum random number generation. Or for example, this can be used for BB84. So it was just an example that I wanted to say. If we have entangled state, we can use that for generation of single photons as well. So now I will begin with one example that we worked on recently, which is Raman process, where we can generate such non-classical states. So our purpose was, like, there are so many non-linear processes which can generate non-classical states. For example, one of the most famous one is spontaneous parametric down conversion. But Raman process is quite important in different aspects of physics. So I will first define the momentum operator for the process, and this was published in this paper. So we have this process where we have this first wing, which is Stokes wing, and this is anti-Stokes. So a pump photon, which is defined here in mode A, like by this annihilation operator AL, in like the wave vector KL, and then it annihilates to generate a Stokes photon with a phonon, and this is governed by this coupling constant GS, and that phonon can contribute in generation of anti-Stokes with the help of annihilation of another pump photon. So this is the model that we used. In addition, we assume that the pump is strong, and we also assume there is only we assume a bath for phonon and which causes damping in the phonon mode. So we were interested in the Raman process because it is quite used in quantum technology, different aspects of quantum information and quantum technologies. For example, for quantum repeaters and quantum memory and quantum random number generation, as I just mentioned. And so our interest was in the sense of generation of photon pair. So whatever experiments have been carried out in the past, they were for single pair of photons. But we were interested in like more mesoscopic regime, and where we can generate close to few tens of photon pairs. So I want to show this example, which is for quantum memory, just for one example that how it works. So these are the pulses which are coming from the pump, and it generates one sequentially, like the one right, they call it right pulse, which generate Stokes, and then a read pulse, which generates anti-Stokes. So these consecutive pulses are coming, and so Stokes and anti-Stokes are generated orthogonal to the incoming pump beam, so that they can be distinguished. And then here they were studying the correlations between them. But one more thing that I wanted to show here is the pump, which additional pumps is pumped here from this direction, which initializes the this gas atomic ensemble here with all the atoms in the ground state, so that it works like more for quantum memory. So I will later come back to it, like how it is effective in generation of photon pairs. So another example, which is more closer to quantum information, is this, that in the same way there is a write and read pulse, but here time bin qubit are prepared, and then after this here, this is the time evolution of this thing. Then this sample, which is Raman active sample, which generates Stokes anti-Stokes in orthogonal polarization to the input, and after this time bin, that this entangled state is prepared, and then this was used for to check Bell correlation between them. But what I want to show that it is these kind of experiments are done this way. So in our case, we yes.
Here's a question. Can I go back to the previous slide?
Yeah. Yes.
These numbers that you have, like 800 nanometers, 723 nanometers, what is the system for which these are the characteristic frequencies or wavelengths?
So I'm sorry, I don't remember the Raman active sample here, but the purpose here was that they wanted to do device independent spectroscopy. That's what their idea was. So what they meant was more generally they said it should be applicable to all the samples, but I don't remember the sample here. But there are few other papers that I remember that which were more closer to that, which I will later mention.
Yeah.
No, I was just asking me, is it important that these wavelengths are in this like 700 range? Or you can do this for other frequencies also.
So they depend on the sample actually.
Sure. I mean, of course, it depends on the sample, but the question is whether, let's say, can I do this for like 1,000 nanometers, or is it like restricted to like in the visible?
So I think it is in the visible, and because we want to access the vibrational band. So as I have shown here, this is is also shown here. So this transition is electronic transition between like ground state to excited states, but then this is vibrational transition between G to S that we want to exploit. So these are generally like the in the optical like visible range, but so yes, that I have seen mostly there.
This setup says that that's cesium, right? So if you go to that setup,
can you repeat, please?
Can you go one slide back?
Yes.
In this atomic ensemble that's written on the top, that's cesium, right? So
yes.
Probably the next one is also cesium, but those are unrelated.
The next experiment.
Yeah, are these two related or?
No, these are two separate experiments, but usually for quantum memory and for memory they have preferred cesium. But generally, that for photon generation that we found, unlike that we people prefer now, is more like graphene seeds, because I will show later why they are advantageous, because we require more stronger anti-Stokes coupling relative to Stokes coupling, and graphene usually gives that.
So how does it work as a memory?
Work as?
How does this system work as a memory?
Yeah, so as I show here, so first pulse stores its state here, and then once the next pulse that you send, then it like the right pulse stores the state of the input photon in
Why
this vibration
does,
here.
why does the first pulse help you to
Yeah.
store the state there?
Yeah, so for example, the first pulse is coming, so it stores in the vibrational band vibration. It stores its energy in that in the phone on mode, and we know that because we get a probe, we get information like there is a Stokes photon, so we know that now it is stored. Then when the next pulse comes, then we have which we call read pulse. So this brings that back to the ground state, and then this generates anti-Stokes, and anti-Stokes has the polarization, which yeah.
I
So
understand.
that's it.
What's
Yeah,
the
yeah.
physics behind it? That why does it store the
Why doesn't it
information?
like decay? Why doesn't it like spontaneously?
Why doesn't it decay?
So you mean the vibrational decay. So it is for very short time. So the efforts are to increase the time like for memory. So it is, so there are still, it is not very efficient, but it is like comparable to some other quantum memories. So the efforts are, yeah, to increase the time that we can store it for.
Are there like no other modes nearby for it to decay into?
It can decay, but sometimes what it works is like you
Like
repeat it multiple times. So most of these are like the experiments are done in the lab, so they are repeated multiple times, but it is one of the proof of principle experiment.
but is the lifetime like milliseconds or microseconds or nanoseconds? Like, what is the uh, order of
So
magnitude?
I I would say the best one that I remember was in NV Center. So I don't remember actually what was the time here, but I would say it it was not, certainly it was not more than a second, because the best one that I have seen for the memory was NV Center base, where it was stored in that, and they were able to do it in nuclear space.
And how high do you need this to be so that before you can like start using this as like some real memory?
So it depends on the purposes. For example, for some cryptographic things where we require to store, suppose, for example, I was showing telling about the teleportation, or for example, dense coding. So it requires to be as long as it takes for photon to travel from Alice to Bob, for example. So it depends on where are we going to use it, but it can be reduced by using a source in between, and then using quantum repeaters. But effective quantum repeaters require us to share entangled states in the network, and then measure on them. So it is, the longer it is, the better, kind of. So even the repeaters that are used at the moment, they are trusted node. So if it can store, then it will be more better, because then we can transmit information for longer distances. So I will say we are still in the initial stages, and we would like it to have like very long in that sense, maybe 1,000 times or even more than that.
Sure. What extra effort one should take to enhance
Yes.
the memory time in this modeling?
Uh, so what I have also found in our results, and I will later shine on it. One is to keep temperature low, because we require to have lesser thermal bath interaction. So, and the initial phonon, because if we see here, the initial phonon will bring the chaotic nature of it, like, because what we want is a coherent transfer of energy from the pump to phonon mode and later to anti-Stokes. Uh, so so it requires to have like low temperature, and strong coupling, strong anti-Stokes coupling.
So you see that this is basically a negative effect, because most of the people who are trying hard to generate a memory which may work kindly at room temperature. So if you need
Yes.
at a low temperature, I mean, this is not very useful.
It's impractical.
It's impractical.
So, but it is, yeah, I agree with you. But it is one of the first memories that was proposed and that was realized in experiment. So, for example, this you can see the first one, long distance quantum communication, which is 2001 paper. So it was the first one that where DLCZ, this long distance communication, was realized. So this may not be the last one, but what I am proposing is not for quantum memory. I'm proposing more for entanglement generation. So more like SPDC, another source which can generate analogous to SPDC like signal idler photon pairs.
Fine, fine. Now, in comparison to SPDC, how efficient is it for generating entangled states?
Yeah, that I will have to move forward to show that.
Okay, yeah, go ahead. We'll see. Go ahead.
So we obtain so I will not go in detail of the mathematical equations that I'm showing, but I'm showing so that I can show some things are about them.
Derive these equations?
What's that?
How does one derive these equations?
So we use this momentum operator that I have shown earlier, this momentum operator. We use this in this Heisenberg equations, and we obtain these coupled equation, linear equations for operators. And what I wanted to show here is these are linear equations because we used strong pump conditions, and that makes it feasible to solve them exactly, and then obtain, because these are linear, so we can obtain a Gaussian solution from that, Gaussian characteristic function from that. But one more thing that is quite interesting here is, so we have this n quantity, which is constant of motion. So it is sometimes visible in the results that how it is manifested in different ways. So we have these coupled equations. We obtain the solution of these coupled equations in this form, where these operators now are written in interaction picture, and then we have the functional forms of the coefficients are in this form. So there are few parameters which are important, as I mentioned, is the anti-Stokes coupling, ratio of the anti-Stokes coupling to Stokes coupling. And this ratio was quite important in what we studied. And
can you go back to the previous one?
Yeah, yes.
Yeah, yeah. So
yes.
Your equation that you have started with is AZ can be ASZ, AAZ, something like that, right? Anyone?
Yes.
Okay.
Yes. So these are, this is Stokes, this is anti-Stokes, this is phonon, and this is the reservoir for phonon. Yes.
So what you did is, so from this equation, what did you do? How did you get these differential equations that you mentioned above? These 4 differential equations.
So we had this G, which I have shown earlier. I can go back to slides. This is our G. So what we use is G plus GR, which is for reservoir. So we use that and we substitute that in this commutator, and we take this, we solve this.
In this equation, GZ is just GZ or GZ plus GRZ?
So it is GZ plus GRZ.
Okay. So in this Heisenberg equation, it is GZ plus GRZ, right?
Yes. So
okay.
So we wrote here, yes.
Okay, and then you basically took the reductions, right?
Yeah, yes. So we just solve it and then we get this. Yes.
Okay. Now, what sort of dynamics does it provide for these A operators? Is it, does it have some memory or no?
So for that we use Wigner-Wyskoff approximation. So it doesn't have memory. So it is like in Markovian regime.
And the interaction is weak or strong?
Interaction is weak. Yes, interaction is weak, and we also have strong pumping. So effectively, what interaction constant we are getting is actually product of this. So this alpha is pump power, square root of pump power, and phase does not, means phase plays a role, but we have used the phase which gives us maximum transfer of energy. So effectively, it is product of this coupling, like Stokes or anti-Stokes coupling, product with the pump power. So it is like our effective
So then
interaction
it
cost.
need not be weak, right?
Yes. So in that sense, but our effective coupling, because it is effective coupling, but still our coupling is very weak because this is third order. Raman is already third order process, so it is going to be weak. Yeah.
Okay, so you choose your pump power such that the total, the GSA will be weak.
So actually, even if we increase pump power, the GSAs are still like tilde GS is still so weak that like it will be 1 in maybe 10 million that will be transferred. So in that sense, it remains very weak process.
Okay, yeah, okay, continue.
So here I give some examples of the materials, especially because I will be stressing that there is we prefer epsilon greater than 1. So I listed here some examples where it is greater than 1. For example, diamond has 5.8, and this is some experimental work where it was shown. And these two are two different kinds of graphene thin films where this epsilon is very high. And so in addition to that, there are some experiments where it was shown for water as well, but I assume they haven't given the value of epsilon. Like it was, they didn't provide sufficient parameters that we can estimate the value of epsilon, so we didn't use that. And so we considered three scenarios. And so for once we have the operator evaluation of operator, so for obtaining the dynamics, so we assume all the modes, Stokes, anti-Stokes, in three scenarios. We either assume them all of them, all three in vacuum. In the first case, because that is most like trivial, or then we will realize that is the most ideal scenario, and we assume that there is no like reservoir. And then we consider the second case where we assume non-zero thermal vibrations, but without reservoir. But then in the end, we consider the effect of reservoir as well, because we want to see which is more which parameter we should control more. So, as a, yeah.
Part of the graphene that you had in the previous slide. So
Can you please repeat?
So is it the case that if you have like a flat band system, then this epsilon is large? So twisted violet graphene, example of a flat band, it has an almost flat band. Is that the epsilon is large?
So I think if that would have been the case, I do not think in along that line. So I can't comment on that, because I thought it has something to do with the like, because diamond has more than stronger anti-Stokes coupling than Stokes. And then I thought when we go to some other carbon material which are like prepared like artificially, then they have good, but I didn't think along the line you suggested, but I will think about it. So as I mentioned, we have because we had coupled linear equations, so we can obtain the characteristic function which is Gaussian. So which by which I mean that we only have up to second order momentums, second order terms, and so where different terms are defined here. So these coefficients are as I have already shown in in the previous slides. So the two cases that I mentioned are important is like the value of epsilon. So this is the first case where we are considering all the states in the vacuum initially. So we found that for epsilon less than equal to 1, the solution is defined by hyperbolic functions. For this is the 3 parameters which non-zero parameters, because all the other quantities in the characteristic function were 0. And so which these are defined by hyperbolic function, but when epsilon is greater than 1, we have these quantities defined by like trigonometric functions. And for our analysis, we define this parameter alpha ln, because this is dimensionless, and it is composed of all the quantities, that coupling constants and all. And so it is, but our effort was to keep it dimensionless, so we decided the length of the crystal as L, and we are looking at the dynamics inside the crystal. So when we will have Z equal to 1, so it means that we are talking about like how the states are coming out of the crystal, kind of. So now we get two regimes here. So one is epsilon less than 1 and epsilon greater than 1. So as I mentioned, in the less than 1, this is defined by hyperbolic function. So we have this average photon numbers in signal, and as this Stokes and anti-Stokes increasing monotonously. But our effort was to generate photon pairs. So this is not of our interest. That's what I said. We require epsilon greater than 1 means we require anti-Stokes coupling is stronger than Stokes coupling. And here we have this oscillatory behavior because of the trigonometric functions. And here there are two important this rescaled pump power, which is this one for the maxima and for the minima. So the nature is something like, here we obtain the exact pairs, photon pairs in Stokes anti-Stokes, and here they return to their initial state. So the nature what we found was it could be explained because the phonon mode has periodicity, which is period 1/2 of that of Stokes and anti-Stokes. So phonon mode returns to its initial state here, and when this is its maxima, but phonon mode again returns here to its initial state. So that's why we have this maxima, which is like exact pairs. So we identified these maxima and minima, and then because we are working in Heisenberg picture, so for this case we were able to obtain the state, because as I mentioned, the phonon mode returns to its original state. That's why our two modes, Stokes and anti-Stokes, they are in pure state, because we started with the pure state. So our reduced state is again pure state, because it is not correlated with phonon mode anymore. And then we were able to write the wave function for that. And in that case, we can see it has similarity with SPDC, but there is one extra phase. So which plays a role in where I found it relevant is in photon number distributions, it doesn't show anything because this is just a phase parameter. But if we want to do teleportation using this state, for example, then we have to use different displacement operator. So there is a small difference here. But then generally, this is the state at maximum, which can be given by this photon number distribution, which is completely diagonal, like a signal idler photon number distribution in SPDC. But as I mentioned, like at 1/2 of the maxima, where because we are considering the ideal scenario, so the Stokes number of photons in Stokes can be greater than anti-Stokes, but not other way around. So we see that there are some non-zero bars on the one side, but not on the other. So corresponding to these two cases, we can also obtain the integrated intensity distributions, because we wanted to show like this photon number distribution is non-classical and contains some non-classicality into it. So what I'm showing in the equation here, this equation is, I have started with quasi-probability distribution of P function. So this is the marginal for two beams, because when we consider generally, because we were interested in the quantities that can be tested later in the experiments. So this quantity is, and when we go for the experiments and we are interested in mesoscopic regime later on, so we see that most of the time when states are multimode, so phase do not play that important role. So we can get most of the information from the marginals of the distributions. So what I am saying is integrated intensity it is integrated over the phase of the two modes. So what we have is the intensity distributions. So this integrated intensity distribution is defined in terms of this photon number distribution. And so these are S is S ordered. So when we order, so this can give us the like non-classicality depth, which is the amount of noise, Gaussian noise that can be added to destroy the non-classicality. So that is one of the measures of non-classicality. And the negative values of this integrated intensity distributions gives us non-classical feature. So here in the plot, which is again corresponding to the two photon number distribution, the white area is the negative region and the black is the positive region. So we can see there are difference in the photon, like the integrated intensity distributions, and we obtained this for the same value of S parameter, which is greater than 0, because these are Gaussian in nature. So then I will come to case 2 and 3 and how they affect the photon number, photon pairs that.
Can you hear me?
Yes. Yeah, yes, sir.
If you go to the state that has been generated,
Yes, sir.
State with Stokes and anti-Stokes.
Yeah, yes, sir. This one.
Yes. So what are the reduced states of, let's say, Stokes mode and let's say the anti-Stokes modes?
So reduced Stokes and anti-Stokes here are thermal, and same as SPDC. Yes, thermal, because this is the distribution as I had written here. It is, so B is actually average photon number, which is so this distribution is thermal distribution. So that's why it behaves similar to the same way as SPDC, because SPDC also has the thermal distribution, and when we take the marginals, it is defined by thermal distributions, and that's why we don't get in SPDC like.
Okay, so now it is assumed that this is for the sake of argument, that therefore the state that you have generated with this Stokes and anti-Stokes field is basically two more squeezed vacuum state, but with these relative phases, right?
Yes.
So let's take a two more squeezed vacuum state, and then I apply on one mode of them. Let's say, some phase which is dependent upon the photon number. Let's say for the sake of argument, okay, so I'll definitely get this state, right?
Yes, exactly this state, yes.
Okay, so then why do you need all these complicated processes to generate such a state?
So we want to have so this is the ideal scenario. As I mentioned, our initial phonon are in vacuum, which is very ideal, which can be obtained, as I mentioned, in the memory case, that by pumping that and forcing that all the atoms in the ground.
Non-ideal case can happen also for the.
Yeah. So the idea is like, can it be generated like the photon? Because there are some experiments which show in a few pair, like photon pair, one pair of photon in anti-Stokes and Stokes can be generated. So our idea was whether few pairs, like tens of pairs, can be generated. So the idea is we can do it with SPDC, but is there some other scope where we can generate the same kind of states? And if the Raman is quite we say well studied in different aspects, so the idea was whether we can generate this in this.
No, you see, in SPDC itself, which generates this two more squeeze vacuum state in principle. So I apply this the photon number dependent phases. Okay, let's
Yes,
say in the idler mode, I apply this thing. I'll get
yes,
this thing.
yes. Yeah, that's true. But this is how we found this, but we don't expect it will be realizable. Like in experiments, I we think that it will be very difficult to obtain this pure state. What we will get will be more like maybe the photon number distribution close to the diagonal,
Mhm.
and or like more like this. It will be maybe tilted on one side if we are able to have uh, the phonon mode in vacuum, because what we are saying is the pump power. So it is very so it may be difficult to achieve this pump power. This may be very strong because it depends on so many experimental parameters. So it depends on focusing, it depends on the material, it depends on so many other things. So it is like maybe what we are showing the theory, the periodicity. Someone may not be able to see the whole periodicity. That
Question.
maybe in the yeah,
We already know how SPDC works, how SPDC generates two more squeeze background state kind of thing. And we also
yeah.
know what is efficiency. So based upon the pump power and other things. So unless one can compare, the efficiency of a generation of the state that you mentioned with that of
Yeah.
SPD, how does one know that this is going to be useful or not?
So we do think the efficiency will not be as same as SPDC, but we compared in our work. We compared if the intensity of the output of SPDC is same of the average of Stokes and anti-Stokes here, then we found that most of the non-classical T and everything that we studied was comparable, was same. Because
How about this uh, what is that called? Heralding. For SPDC, we can herald one beam to
yes,
a single photon. So what about heralding here? How does it work?
yeah,
Or how?
it should work the same way. Heralding should work the same way because without heralding, the states are in marginal states are in thermal distribution here. So by heralding, we can generate suppose-onion or single photon sources because that
Okay.
will depend on the direction
Now
efficiency of
I
the
use
technique.
your source for single photon, for generating single photon through heralding. And then if I
Yes.
use in this Hongo-Mendel scenario, so do you get the similar effect?
So for Hangu Mandal, after heralding,
Yeah, so you will have to take two such sources, okay?
yes, yeah.
You herald
So
each of these.
so yeah, so that will depend on whether we are using both Stokes photons or both anti-Stokes, because we know there is a small difference in their frequency. And so, or if we want to do that, if we are using one Stokes, one anti-Stokes, in that case, we will have to remove that difference, because for Hongo Mendel to work, we need at the beam splitter when they are coming, they should be like identical, or they should not be distinguishable. Indistinguishability should be there. So in that sense, it will work. Hongo Mendel should work
Okay, yeah, you
because
can
it is
proceed.
already shown with some other works, especially in the sense of MDI QKD, measurement device QKD, where two different laser sources can generate, which will interfere and show Hongo-Mendel kind of.
Okay, yeah, you proceed. Yes.
So I had shown this ideal photon number distribution diagonal, and but what happens when we have non-zero phonons initially and then damping as well. So the ideal scenario is here represented by the green lines. The smooth lines are for Stokes and dashed ones are for anti-Stokes. So in the green lines, we can see that we had this peak point that we discussed where there is exact photon pairs, but the anti-Stokes photon number always remains less than Stokes photon number. But when we go for initial non-zero thermal phonons without decay, then we have in between the phonon, uh, the free phonons or non-zero initial phonons, they contribute to the anti-Stokes, and that's why anti-Stokes is stronger than Stokes. But at this peak, as I mentioned, the phonon mode returns to its initial state. So we are left with this exact pair. So the initial phonon pairs do not affect initial free non-zero phonons do not affect the photon pairing as long as there is no damping. So, but when the damping is there in the phonon mode, then it destroys this, and then it is difficult to obtain it. So there are two parameters to control. Is one is to have phonon initial phonon to have less, because then and the other is to control the damping, so which will require to work in smaller times in that sense. So then we analogous to this, we studied some quantities which quantify the correlations between Stokes and anti-Stokes, analogous to what the way we study for SPDC. For example, G2 parameter, which is cross correlation function. So and normal, where we see in the denominator this is normalized by the intensity. But I have shown that at certain point the Stokes anti-Stokes phonon number returns to its initial state, which is 0, and there it blows up. That's why sometimes it is not very good quantity to measure in the experiments. But in view of this, in addition to Cauchy-Schwarz inequality that is satisfied in some of the experiments, especially that I was mentioning about the water with water, where they measured this G2 in experiment with Cauchy-Schwarz inequality, and then in our case we could see that in view of G2 greater than 2 in presence of due to Cauchy-Schwarz inequality should reveal non-classicality. And this behaves the same way because it is always more than 2. And at the peak, when we have this is the behavior depending upon the denominator is deciding this, because this is blowing up. But the more important quantity for especially for photon pairs that we use in our labs or our experiment for with the SPDC in mesoscopic regime is this R parameter. So it is subsort noise. So it is the difference in it is the variance of the difference in photon numbers in two beams, which is in the denominator is short noise limit. So whenever the quantity is less than 1, so we have the short noise subsort, which we call subsort noise, and the quantity always remains less than 1. And we can see that when the photon pairs were there, it becomes 0, which is ideal. And when they are both 0, then when they return to initial state, it is 1. And we can see that with increase from like for non-zero phonons, it increases slightly, but the phonon decay is more important parameter. And then we quantified the non-classical, the entanglement using the Simon criteria, where we obtain the symmetric covariance matrix, and from that we obtain the negative eigenvalue. We obtain this value for eigenvalues which are less than 1, and then from that we obtain this, and which shows us the similar behavior that entanglement is maximum for suitable powers. But what we were also interested here is, as I mentioned, we have tripartite state. So we obtain the purity of the reduced bipartite Stokes anti-Stokes. And here we can see that we can compare it with the rest of the plots, that we can see the purity has period which is half of that of other quantities, because as I mentioned, this depends on the period of phonon mode. And so it shows that it is most of the time the Stokes anti-Stokes modes are not in pure state, because for pure state we know that if entanglement is there, we know that this entanglement is feature of stronger correlations like steering and bell type correlations. So in our case, because the state was mostly like mixed, so we obtained these quantities separately. So we numerically we checked this bell type violation, which is defined in terms of these displaced parity operators for different values of beta s, s1 and beta s2, which are
yes. Can you go to the previous slide?
Yes.
So whenever you have these phonon modes, So basically the state that will be generated is not a pure state, right?
Yes, sir.
Okay. So then
But
you,
at this peak, at this
yeah,
optimum pump power where we are at peak, because
yes,
phonon
right,
mode returns to its original, so then it is pure. Yes.
right, right. So let's say in the generic case where it is a mixed state. So you apply the Simon's criteria then, right? For
Yes.
evaluating the
No,
entanglement.
entanglement. Yeah, yes.
Now, the mixed state that is being generated, these two modes, namely the Stokes and anti-Stokes, I'm sure that this is a two-mode Gaussian state, right?
Yes, sir. It is two mode Gaussian.
So this two-mode Gaussian state, you use Simon's criteria for detecting its entanglement, right?
Yeah, yes.
With this, I think the minimum
Yes, minimum eigenvalue,
symplectic
symplectic
eigen.
eigen. Yeah, yes. Partial transpose
Now,
covariance.
this two-mode Gaussian state, is it a symmetric two-mode or not symmetric?
It is not symmetric. Yeah.
So if it is not
But
symmetric, can you
yeah,
use
yes.
Simon's criteria for entanglement?
So it in generally the later works by Adesho and all, they have used generally, they have proposed this, and they use it for steering as well, which is completely asymmetric in nature. So yes, I think we can use it. Yeah.
Are you sure you can use it?
So I have used it not only for this, but some other states which were completely asymmetric. So even I it does give some lower bound to it. So I
See,
will
this
have to go.
provides it whether the state is entangled or not. That I agree.
Yes. Yeah, yes. Sir.
Symplectic eigenvalue, minimum symplectic eigenvalue.
Yeah, yeah.
Whether it provides your entanglement or not, does Simon's criteria provide that? Even if the state is not symmetric.
I don't remember that. I will have to go and check. Yeah.
Okay, yeah, go ahead. Yes.
So we checked the Bell type correlation because the state was not pure, and we obtained that when the phonon mode was in vacuum or in like some thermal state, uh, but without damping, then we could see the Bell violation. But with the damping, it was difficult to obtain it. But still, in case of steering, which we found that steering was like we observed steering even in presence of damping. But one more thing which is important about steering here, we could see that Stokes mode can steer anti-Stokes mode strongly than the other way around. And steering is also obtained from the covariance symplectic covariance matrix, so determinant of that. So then so we had these results, and we some of the experimentalists here were interested in realizing that, and they were trying to do, because most of the quantities that we have shown here were already like they can be measured for SPDC as we were discussing. So they are interested in doing this experiment for Raman. But in the experiment, when they will go for this mesoscopic regime, it will require to have it multi-mode, because so far we were considering single mode. And so in the future, I want to work on this multi-mode theory for this, where we can analyze this.
Can I ask
Yes.
you one question in regard to this classification or steering? So this mode entangled state that is being generated by this Raman process, these Stokes and anti-Stokes.
Yes.
You want to experiment, of course, you'll have to physically separate out these Stokes and anti-Stokes, right? Otherwise,
Yes.
So in the realistic experimental setup, if someone wants to generate such a state, and then you can do whatever you want, like Bell violation.
Yes.
So in a realistic setup, how far you can take these two modes?
How far you means isolate them?
Isolate them, yes.
So I will have to go back to the first experiment that I was showing, where it was done this way because they were in same polarization. But then using this PBS, these are three filter cavities where these were filters, and then Stokes is obtained here and anti-Stokes is obtained here.
What is the distance between these two Stokes and anti-Stokes in the lab?
So they are certainly very close. It is not here, but in this slide we can see this is 766 and 723 in this experiment.
That is in terms of your frequency.
Yeah,
physically, these two modes.
You mean in the cone? Yeah, you mean in the cone? Yeah. So generally, yeah, they are very close, but because they are in orthogonal polarization with pump, so it is easier to differentiate them with the pump. And then once they are separated, then you have to use dichroic mirrors or something like that because some experiments use dichroic mirror to distinguish, like to obtain them separately, Stokes and anti-Stokes.
Okay. Yeah, you'll have to separate out paths. Otherwise, for communication purpose, angle state will not be of very much useful.
Yeah. They are separated mostly, especially the experiments which are performed for correlations that requires them to be separated, and they are efficiently separated by this kind of filtering using cavities or some dichroic mirrors. So it depends on what available resources they have or what their experiences with that in experiment.
So go ahead. Yes.
So this is so I want to pursue this for multimode theory of this and for the sake which can be used for the experiments. So other aspect is that I am working recently is in
Sorry, Kishore. Can you hear me? So for multimode,
yes, sir.
that you have in mind, how will you generate the multimode states in this Raman process?
So first thing, of course, I will focus on one vibrational band. Yes. And then I have read, because I was working with these twin beams, which requires a lot of work with the multimode theory for SPDC. So it is more like one pump photon is actually generating a signal idler pair. So at one point, we can think that as a kind of three together. So the spectral mode, this can give us spectral and spatial mode of it, because spatial mode will be generally a correlation area, which will be because of not exactly following the phase matching condition. So this can give us an estimate, and this way we can go back and we can estimate that the number of modes in the output, they can be correlated or they can be mapped to the number of modes in pump. So that's what I have in mind.
So, for information processing purpose, it is not only generate multi-mode state, but you'll have to also control the individual modes.
Otherwise, but that's what these modes are not individually addressable, and sometimes we for the analysis of quantum optics we truncate because there could be infinitely many such spatio-temporal, spatio-spectral modes. So we know that some of them are populated and some of them are not. So it is like a long tail. So we cut that and then we assume that number, and then we assume equally populated them. And yes, we can't address them individually, but that is actually very common even in some optomechanical kind of things as well, where they can't address them individually. Yeah.
Okay. Yes. Go ahead.
Yeah. So we were recently interested in this higher order acceptance singularity. So what our purpose was to have quantum consistent models and check whether for multi-mode bosonic systems we can obtain higher order exceptional singularity. So for example, I give an example here for this 3-mode bosonic system. where these three modes, A1, A2, A3, are governed by this second order quadratic Hamiltonian, where we have a beam splitter interaction, which is governed by epsilon. And then there is this parametric kind of, which is SPDC kind of interaction, which is governed by kappa. And this is the source of non-linearity, or this non-linearity will introduce, can introduce non-classicality in the system. So these are three modes, and we can write the Heisenberg-Langevin equations the same way that I have shown previously, where this, so we are writing it in a compact form, where this like vector A is composed of three more, A1, A2, A3, where this block A1, A2, A3 are already A1 dagger. So this is to write it in a compact form, and then we write this M3, which is a dynamical matrix here, and which is defined by 2x2 matrices, which are given here. So we use this because this way we could check, we could use this consistently for a large number of systems, and then we obtained everything, and we show that it is in principle consistent. So this L is Langevin forces, which are defined here. So once we diagonalize M3, and then we obtain from the corresponding eigenvectors, we can obtain the matrix which will diagonalize M3 to obtain this diagonal form of the dynamical matrix. And that same matrix will give us the new basis for these operators B, new operators B, and also Langevin forces, new Langevin forces K. And so in principle, when we have this diagonal omega-3, we can write the equation, this equation, Heisenberg-Langevin equation, in this new transformed basis, and for which we can obtain the solution. And now that solution can be inversed, using the inverse operation, we can get back the solution for A. So I wanted to show this, like this is the consistent way we do it. And so this is the Hamiltonian, for example, and we have, sorry, we have this dynamical matrix M3, and yes, sir.
Hello?
Yes, sir.
So can you go to the previous slide?
Yes.
So what was the purpose of using these Heisenberg-Langevin equation? I mean, why did you start with this? Why not something else?
So we wanted to do everything in Heisenberg picture, and there are studies where people have done it with the master equation, but our purpose was to obtain the spectrum of eigenvalues and eigenvectors and conclude few things about it. For example, we wanted to show how the exceptional singularity or diabolical singularity in the lower orders of the like the annihilation and creation operators can be mapped to corresponding higher order moments, and to estimate them consistently, and to check to keep it quantum consistent, the Langevin forces keep it consistent.
See, the thing is, if you use linear master equation, of course, you can come up with such an equation for E. Okay. In principle, you can come up.
Yes.
When we talk about Langevin equation, there will be some stochasticity. So your Langevin, does it contain also stochasticity?
Yeah, because Langevin forces bring it in picture, because Langevin forces have their own properties.
Right. So what sort of form these Langevin forces you have considered?
So far I didn't need it, because but when we consider, like when we, in one case we studied the dynamics, and then we were considering all the first order terms like L1 dagger, they are averages are 0. But when the second order terms, they depending on the damping or the amplification, they are changed. So the second order quantities are non-zero depending upon that. because we are not considering a squeezed reservoir. So our reservoir is either damped or amplified. But in this scenario that I'm considering discussing at the moment, so I'm not showing today the dynamics part, which I will discuss tomorrow with an example. So that will be discussed tomorrow.
Okay, yeah, go ahead.
So what I want to show is this M3. From M3, we can obtain corresponding eigenvalues, which are obtained like this. And we assumed a special condition here between the relation between the damping of these three modes. And here we parameterize these. This is just for simplification to write the notation. And so we can see that as I mentioned, that these block forms were consistently used, and the eigenvalues are this pair of this off-diagonal, this coupling matrix. So these are in plus and minus form. So, and the eigenvectors are obtained here. So there is one thing that I wanted to show from is the eigenvalues we can see is beta, and which is actually depending on this zeta square. So whenever the eigenvalue, we are substituting this zeta by the eigenvalues, so square becomes always positive. So the eigenvalues are always like, there are only 3 unique eigenvalues. But when we go to eigenvectors, there is a linear term of z. So this is phase dependent on the eigenvalue, and we obtain. So that's why when we write the explicit form, so we obtain 2 like 6 so we have unique eigenvalues. Like there are so 2 sets of 3 eigenvalues, but there are 6 eigenvectors because there is no repetition. So this is what we have, 1 eigenvalue with 2 eigenvectors. So this is diabolical degeneracy. And there, so further, if we see, if beta is 0, then all 3 eigenvalues become same, and the eigenvectors also become same. So we have this degeneracy. So where all the eigenvalues, the real part becomes 0, and the eigenvectors become same. But as I mentioned, there still remain 1 eigenvalue corresponding to 2 eigenvectors. So we have the order. So first, before going to there, I would show that this beta condition in the parameter space is, we have 3 parameters, kappa, gamma minus, which is just this difference of these decays. So this is defined by this, beta is in the parameter space defined by this ellipse, which is defined here. So we say this is the exceptional point on this, any point on this ellipse is exceptional, this singularity, and other than that we have we don't see that. So what I want to say is this: we have the imaginary part is same, and the real part was in pair of minus and plus. So we assign the eigenvalues in such a way that the pair plus and minus. So B1 is 0, so B1 dagger is also 0. And then B2 and B2 dagger are minus plus beta. But all these at exceptional singularity, beta is equal to 0. So all these become 0. So, but these 3 gives us 1 exceptional point, and the other 3 gives us other exceptional point, and they are overlapping on each other. So genuine exceptional degeneracy is 3 times. And when they are collectively taken together, then we have diabolical degeneracy, which is two of that. So we have 3rd order exceptional degeneracy and 2nd order diabolical degeneracy. And so what I will discuss in more detail tomorrow will be that if we have this degeneracy, which is 2nd order diabolical and 3rd order exceptional in the operators, then their corresponding higher order movements have corresponding higher order degeneracy, and which we know from the from some existing literature that nth order exceptional degeneracy leads to nth root splitting of eigenvalues when the system is at its exceptional point. And the other thing that I will discuss more detail tomorrow will be this how the genuine order of degeneracies can be calculated, because if we should be taking care of the equivalence of two operators when considered the commutation relations and the like commutating behavior of them. So this is an example in one of our case where we had second order exceptional degeneracy, and we can see the originally our because we considered this, the real part was 0. So when we have this small perturbation, and with that our splitting of eigenvalues in this way, and this splitting can be useful for sensing, because this can be measured. If there is a small perturbation, this leads to a large signal. So what I'm pursuing at the moment is because we have seen this in higher order exceptional singularity in some multimode bosonic systems. We are interested in at the moment in seeing their advantage in generation of multipartite entanglement, and then for sensing as well. So other than that, we have studied some quantum state engineering in the past, where we focused on their role or advancement in metrology and quantum communication. One of these operations, which I mentioned in the beginning, how photon addition leads to non-classical states. So similarly, there are some other operations, for example, photon subtraction, which is like if using a beam splitter, if we use a state rho and a photon, a post-selected photon here will tell us that the state here is photon subtracted state. So all these operations collectively are useful for quantum entanglement distillation, etc. And so this is one of the recent works that we came across, where they have experimentally performed photon subtraction on two-mode squeezed vacuum state. So two-mode squeezed vacuum is this, which is output of spontaneous parametric down conversion, and the distribution is given by thermal distribution. And here it was for 0 photon subtraction, 1 photon subtraction, symmetric subtraction from 1 from both beams, 2 from both beams, and 3 from both beams. And we can see that the original distribution, which remains close for 0 photon subtraction, which is close to thermal, but with the higher number of photon subtraction, it start moving towards Poisson distribution. But one thing which was important here was it never went. It did not become narrower than Poisson distribution, so it did not become sub-Poissonian.
So when you have 0 photon subtraction, why
yes,
the photon subtraction changes?
Can you please repeat, sir?
When you have 0 photon subtraction from these two more squeezed vacuums, why the photon number changes?
So it is not changing because it is working more like attenuation, noiseless attenuation. So the average photon number slightly decreases, but it doesn't change much the photon number distribution.
No, that is okay. But even if there is a small change, why does it happen?
Due to 0 photon subtraction?
Yes.
Because we are using a beam splitter, and even if we assume the ideal detectors, so what we are getting, that because this is very highly transmitting beam splitter, so what we are getting in the transmitted part, it has intensity slightly lesser than that of the input beam. And also we are using a correlated beam because it is squeezed two-mode squeezed vacuum. But when we are not detecting anything, so we are not breaking any pairs in that sense. So most of the pairs are still there in the transmitted beams.
If I only take the successful events, like
yes, sir.
only consider those events where my detector does not detect any photon.
Yes, sir.
So in that case, there will be, of course, the dot count, detection inefficiency.
Yeah.
So if I forget about that, still one can get to see some changes, right? Why does that happen?
Yeah. So, so I don't think distribution changes much because it will still remain close to thermal. So average photon number will slightly decrease but that can also be obtained, like that will depend on the transmittivity of the beam splitter. But average photon number will decrease, but the distribution will remain same.
Okay. Okay. Yeah. Go ahead.
So this motivated us. This was this Magna Luisa work that I was showing that what they obtained, but it did not become narrower than Poisson distribution. So this motivated us to check for why is the case, and that motivated us to check if we have mixture of such two mode squeezed vacuum states, for example in twin beams, and this multi-mode state, and our theoretical analysis told us that there will be three interesting scenarios. One will be that both are transmitted, and when both are transmitted, this is something like what is used in entanglement distillation. But when one of them is measured, then its pair should lead to local non-classicality in the corresponding beam. So this is something like how we visualize it. So this is the signal and idler, for example. And if this post-selected photon here will tell us photon subtraction and in signal and photon subtraction in idler. So this way we get photon subtracted beam. So so before going to the experiment, I will just show what our theoretical analysis said. So, so for this, this is our photon number distribution for twin beam, which has this. This is our Mendel-Rice formula, which gives us multi-mode photon number distribution. And so this is thermal distribution for multi-mode states, where we assume that there are, for example, MP paired photons. But there could be in experiment, as you mentioned, there could be some unpaired part, very small, negligible, but still like that, and which is again in thermal, so which will be again in multi-mode. So the distribution is same. So this is multi-mode thermal contribution in signal and multi-mode thermal contribution in idler, and this is the paired. So we have this total photon number distribution this way. And from this, in experiment, what we obtain is this 4-dimensional frequency histogram, which is obtained by this photon number distribution, photon number measurement on the these photon subtracted, where this is subtracted counts, and then two-dimensional photon number distribution, where this matrix corresponds to photon number resolving detection with the detection efficiencies eta A and all. So for in theory, what we so this is the photon number distribution which is obtained with a twin beam. We have this is binomial distribution due to the beam splitter, and then following that measurement on the reflected part. So this way we obtain the photon number distribution for photon subtracted beams, and then performing measurement we obtain the 4-dimensional frequency histogram. So in the experiment, this is the BPO crystal. After laser pumping, it generates like signal idler, and we have this. This is the photon number resolving detection using ICCD cameras, where this is the signal photo count and this is idler photo count, and these bars are for subtracted beams in signal and idler respectively. And so our theoretical analysis told us, so we use two quantities for that. One is R parameter that I have just shown. This is subshot noise parameter, and this is Poissonian characteristic is measured by marginal Fano factor, where the denominator is average photon number for coherent state to show coherent state limit, and then numerator is variance in photon number. And I had shown earlier that like how G2 we measure G2 for anti-bunching, and which is also closely connected with what we have in like for what we obtain from Fano factor that can be mapped to G2 parameter. But we use Fano factor because it is independent of the number of modes. both these quantities do not depend on the number of modes. And so this is what we obtain with ideal detectors. If we have ideal detectors, we start with 100 of modes with average population population 0.1. So 100 modes with average photon number 0.1 in each, and there is no noise in the signal and idler. Yeah. So without losing much correlations, we can induce this local non-classicality, which was not observed in the previous experiment. And we wanted to have this motivation for the experimentalist as well, and we who had like close to 1/4 detection efficiency, and we show that yes, this can be realized experimentally. And so we have some less than 1 value for marginal Fano factor, which is non-classical feature. But of course, we lose a lot of correlation in the because of the detection efficiency. So I want to compare that with what the experiment of the Magna-Loaiza was, where they used one mode beam, because it was one paired mode, so it means 2-mode squeeze vacuum. So we consider the same population, same average photon number, and we found that it is relatively difficult to obtain marginal in like non-classicality in the marginal field, because we can see that it is mostly greater than 1, and it becomes less than 1 only for very large photon number subtraction, which was not carried out in their experiment. So it is relatively difficult to achieve that in marginal in single 2-mode squeezed vacuum than it is in multi-mode thermal field, multi-mode twin beam. So the reason that is because as I showed in the experiment, that with each photon subtraction, they were going from thermal distribution towards Poisson distribution. But multi-mode fields already are closer to Poisson distribution than thermal distribution. And that's why with each photon subtraction, it is relatively easier to push the distribution from to below sub-Poissonian or below Poisson limit and to become sub-Poissonian in nature. So that's why, in this sense, multi-mode photon subtraction in twin beams is advantageous. So this is some experimental proof that in some cases when there is a so first we generated this twin beam which had on average 8 photon pairs and small signal and idler noise photons, and so that beam transmittivity in the signal and idler was comparable, 0.49 close to 0.5, and we can see that the R parameter, which should be between 0 and 1, shows correlations which remains comparable, like which remains close to 0.5, and we can say that with increase in photon subtraction from idler, going from red, green, blue to black, this is decrease means this quantity is increasing, which means correlations are decreasing. And so similarly with CS, which is a subtraction of photons from signal, this is decreasing, which is expected, because with photon subtraction, it is the local non-classicality is generated at the cost of correlations. So when we subtract large number of photons from signal, it doesn't help in generation of non-classicality in signal, because non-classicality is like induced because of measurement in signal in the idler, or the other way around. So we see that going from red to black, we are increasing the photon subtraction in idler, which is leaving lone photons, corresponding lone pairs in the signal, which leads to non-classicality in signal beam. And so as I mentioned, we are using these quantities because they have like they behave the same way for individual mode as the compound mode. And so we also verified this with the close to ideal detection, which could be mimicked exploiting the spatial correlations in ICCT cameras, because I said the twin beams generate spatial correlations as well, and then exploiting that, for example, here we were varying different transmittivity, but these are the cases I want to compare, the red and black. So red one is for 0.2 transmittivity, and the black one is the same case, but filtered like cases with the ideal detection efficiencies, which is when we had the exact pair that filtered in the signal and idler beam. And we can see that the Fano factor is very good, like it is 0.5, and the correlations are much stronger as well. So we don't lose too much correlations if we have ideal detectors. So these states have applications in quantum cryptography. For example, we have also done some other experiments where we had done this for photon addition, photon subtraction in one beam, or some single and two mode states, two beam states. And so these operations have applications. For example, this quantum cryptography, where they use photon addition in thermal mode, single mode thermal state, and that addition they used in twin beam for quantum cryptography. And the other application is in entangled photon virtual state spectroscopy, where entangled signal and idler beam, signal and idler photons, they pass through the sample and they give information about the excited states which are not accessible otherwise in the spectroscopy. But we, in our case, we expect that that because the photon number fluctuations in signal and idler are below Poissonian limit, they should give an advantage in this kind of spectroscopy. And in addition, I have also worked on some quantum cryptography protocols. Theoretically, we designed them, and some of them have led to some experimental realization with small changes. So that I will use that in future for designing such protocols and trying to realize that under some in collaboration with some experimentalists. So in summary, I discussed how Stokes anti-Stokes pairs can be generated in Raman processes, and what are the ideal conditions for that, like stronger anti-Stokes coupling and controlling the thermal population, and etc. Briefly discussed exceptional singularity in 3-mode bosonic system, and then experimental generation of some non-classical states or non-Gaussian states. So thank you.
Thank you. So it is already late. If there are some short questions, you can ask whoever is there.
Hello.
Yeah, hello.
So this is not my field. So so I have I think you explained it. I have a small doubt.
Yes, please.
You said that if you can intuitively explain, not in detail, but just a simple idea, that how is Raman process giving rise to quantum memory? I mean, I did not get that idea. What I understand is that two photons come in, they exchange a phonon, and they go away, right?
No, not that way. What is happening is one photon is coming.
Okay.
And so it generates Stokes photon. So we know that there is a phonon now available in the system.
Exactly.
And
yeah.
phonon has information about the pump. And now when we require it at later time, we send one pump and which uses that phonon to generate anti-Stokes.
That phonon is the memory, you are saying?
Yeah, phonon is the memory, yes.
Okay. Thank you. Okay.
Any other question?
Yeah, hello, Kishore. You mentioned zero photon subtraction. Is that a Gaussian or non-Gaussian operation?
So that is Gaussian. That remains Gaussian.
Yeah. So single photon subtraction can enhance average number of photon, and you mentioned that zero photon subtraction decreases. Why it is like that? Zero photon subtraction, why it decreases? Can it increase the average number of photons under some value of transmissivity and something like that?
For zero photon subtraction?
Yeah, can it increase?
No. I don't think you can increase for zero photon subtraction, but because that will be natural attenuation. So for zero photon subtraction, we don't, and that's why we compare it with the one when we are saying about the one photon subtraction. But in this kind of states, correlated states, we get opposite because of correlations, because when you are subtracting a photon from signal, actually, you are adding its pair in idler. So that behaves more like, if you may have read some works and on this aspect. So for two mode squeezed vacuum, photon subtraction from signal behaves in the same way as photon subtraction from idler. Also, photon addition in idler. So that is
Yes.
what we have shown in one of our works recently, that how subtraction and addition behave in the same way.
So can we tell about non-classicality by seeing the photon number distribution, by measuring the photon number distribution?
Yes, so that's what we have. For example, what we are measuring is photon number distribution.
Mhm.
And from that, we obtain these quantities, which are actually variances and higher order quantities, but they are obtained from photon number distribution only. So
Okay,
we
okay,
do not perform homodyne measurements. We are just
Mhm.
performing photon number resolving detection. And from that, we are concluding everything.
Okay, great. Thank
So
you.
I will discuss this in more detail tomorrow. So
Yes, yes, great. Yeah, thank you.
thank you.
Okay, any other question?
May I ask a question?
Yes,
So,
please.
The Raman memory that you showed, that is, you have experimentally implemented it in with your collaborators, or it is just in a proposal stage?
No. This is not our work. The memory was done by some other people, and I was just showing like how it is the same way we can have population like at the ground state. So that way we can have the initial vacuum phonons. So it was not our work, and I I don't have any collaborator who is interested in quantum memory at the moment, but people are interested in having photon pair generation. So they are in those experiments are in the initial stage. They are still like trying to figure out, and so there is a group in Prague which is ELI, so extremely large this thing, very intense lasers, and they have interest both in spectroscopy as well as, so they want to do this.
I mean, in a kind of continuing what Ajit was asking, like one of the slides you showed, they were implementing it in cesium atomic system. So, is it specific to? I mean, was there some specific reason, or in general, it is possible in other Rydberg atom systems also, like rubidium, etc. That 700, there is a 729 nanometer line available in rubidium vapors as well. So, in general, those results are implementable in more or less all Rydberg atom systems.
I don't have very much knowledge about the quantum memory like experiments in that detail. So I don't know. I'm sorry.
But okay, I mean, in general, for these Raman processes that you are talking about,
Yes.
they are what are the I mean typical candidates for
So for
seeing them?
our kind of purposes, that's what I was saying. For our kind of purposes, diamond is used mostly. Diamond. There are
Okay.
experiments which are done with water, but
Okay.
the highest amount of like anti-Stokes coupling that was shown was for graphene.
Okay.
So I have seen the experiments with cesium for the pair purpose that I have seen: cesium, water, and diamond.
Okay. All right. Thank you.
Thank you.
Yes.
Oh, any other question?
Hello?
Yes.
Yes. Hello.
Yeah, so you might have answered it earlier, but I wanted to ask this. So this generation of photon pair, right? So how much efficient is it compared to these conventional sources like SPDC in PPKTP or BBO crystals?
So if the first intuitive answer will be from the Chi2 and Chi3 processes, because
Yeah,
Raman is Chi3, so it
yeah,
will be less efficient than SPDC.
Okay.
But then because for our theoretical analysis, we are comparing it with the SPDC as well.
Yeah.
So, but those were very different kind of processes. So
Yeah.
and here Stokes anti-Stokes intensities need not be same because they are not
Yeah.
intensity, like they are not photon number paired in that sense. So how we compared was we considered that the SPDC with the same intensity in the output as the average of Stokes and anti-Stokes that is generated. So every time we were comparing that for the amount of non-classicality. So when we reset the peak, because it is same state as SPDC, so then it
Yeah.
becomes comparable. So all the rest of the time, it is certainly the amount of non-classicality and everything is like slightly less than SPDC.
Okay. And resource-wise, is there any comparison, like the resources required in both the cases, in terms of like crystals or pump, etc.?
Okay. I think in SPDC, in one pump, like
Yeah.
one pulse, you get
Yeah.
both the pairs. But here you get it that in two consecutive pulses.
Oh, so you require two pulses.
Yes, if you are visualizing in the pulse regime, but if you are
Yeah.
working in the continuous, then it is a different thing. But if you may have seen the experiments from the beginning itself, like for the memory itself, one is for write and one is for read. So
Yeah.
first one actually generates phonon, and the second one uses that phonon for anti-Stokes generation. So if
Okay.
you are going for the pulse one, then it will be something similar.
Okay. Thank you.
Okay, so if there is no more question, let us thank Kishore again. Thank you, Kishore.